Meenu Kumari, thank you so much for joining us here at Perimeter Institute in our beautiful but empty theater. Thanks for joining us.
Thanks a lot for having me.
So Meenu, thank you so much for sitting down with us today. I'm really excited to talk to you. Maybe you can just start by telling us what you do here at Perimeter, what your role is, and also what you're interested in studying.
So I'm a postdoc in the Quantum Information Research Group at Perimeter. I joined in September 2019, and I did my PhD at IQC at the University of Waterloo from September 2014 to August 2019.
So IQC, that's the Institute for Quantum Computing just down the road from here. So is quantum computing part of what you do? You're a theorist, and quantum computing sounds like it's for machines. So can you explain how you're connected to quantum computing?
So my research is in the field of quantum information, using the tools and techniques of quantum information to study other questions in physics. The thing is, quantum computing uses quantum information techniques or quantum processing techniques to build like quantum computer. And then there is other part of quantum information, like so many tools and techniques have been developed in the field of quantum information, which can be used in other fields of physics, like high energy physics or condensed matter physics, to study other questions. So quantum information is basically like world is fundamentally quantum, right? So
so just to interrupt, the world is fundamentally quantum in the sense that underneath everything, quantum mechanics sort of describes how the world works at this small level. If you dig deep enough into anything, you'll get into the quantum realm. Is that fair?
Yeah. So the thing is, like, first classical physics was developed, which is like Newtonian mechanics, Galilean relativity, and then Hamiltonian mechanics, and so on. So those theories describe the world at the macroscopic level very well, actually. But towards the end of 18th century, like around 1890 or something, there were so many phenomena that were discovered experimentally, which the physicists were not able to explain using the formulation of classical physics. So they started to dig into what's going on, trying to understand, for example, photoelectric effect. So around 1920 to 1930, this new formalism of quantum mechanics was developed. And over the years, we have seen that, like, whatever we can predict from the theory of quantum mechanics, most of the experiments that we do today, the results of those experiments can be explained using the theory of quantum mechanics. So that's the thing, that the world is fundamentally quantum, because almost all the experiments at the level of at the microscopic level or at the atomic level basically can be explained using the theory of quantum mechanics, although the formulation of quantum mechanics is quite non-intuitive. So that's a bit of...
So I have a question there. Yeah. So as you started to allude to, there's so many research fields that people work in now that are studying different quantum properties of matter. So you mentioned quantum information, quantum computing. There's also quantum matter, quantum foundations, quantum field theory. There's probably a lot of other fields that have the word quantum in them. So can you just tell us a little bit about that word quantum, and really what are some of those quantum features that are so interesting and confusing as opposed to the features we might be more used to in classical matter?
Yeah, so two of the most intriguing features are the principle of superposition and the principle of entanglement, actually. Schrodinger's cat is a famous example. Like, unless and until you look at it, you don't know whether the cat is dead or alive.
This is the famous thought experiment with the cat in a box, and it's a sort of metaphor for things that can be in one state or another at the same time until they're measured. So you don't know if this cat.
Yeah.
When I was younger, I thought that it was a real cat in a real box in a real experiment. I'm glad to know it's not. So that explains superposition, this idea of things in the quantum world being in a state that's more than one thing at the same time?
Yeah, that's right. So, for example, if you take a quantum coin, a classical coin is either in the state of heads, like if you flip it, it will either, sorry, it is either heads or tails. But quantum coin can be in a superposed state of heads and tails, and then you measure it, and you will get either heads or tails out of your measurement result. But a few, like, you can find probability by measuring it again and again. You will find probabilities of getting heads as well as tails, and using that you can construct the quantum state. So the quantum coin is basically in a superposition state. It is not just only in heads or in tails. Like, quantum mechanics is an ensemble theory. It doesn't describe one single instance of a particle or something. Like, it describes, like, if you do something over and over many times, what will be the output that you will get? Like, what will be the probability of getting?
Right. It works more in likelihood and probability than in exact prediction.
Yeah, that's right. So, like, if you have a quantum coin, like, if you just measure it once and see whether it is heads, you can't really say that whether it is in a superposition state of heads plus tails, or whether it is really heads. You will have to perform the measurement on the multiple copies of the same quantum state again and again to figure out whether it is in a superposition state or not.
And sorry to jump in, but this is part of what confuses a lot of people about quantum mechanics, right? This is because we don't experience that. When we flip a coin, it's always heads or tails.
Yeah, that's right.
Because it's a macro world coin. So it's okay that people are confused by this, right? It's not something we experience.
Yeah, it is very non-intuitive. Like, we don't really observe anything in a superposition state. So that's where quantum foundations come in. Like, we describe a quantum particle using a wave function, which can be in a superposition state, but we don't really observe that wave function. What we observe is probabilities of certain kinds of observables, like any real observable. For example, with this coin, when you measure it, whether it in the basis of head and tail, when you measure it, whether you will get head or a tail, actually. So quantum foundation is like trying to understand what is real versus what we infer out of measurement. So this whole mathematical formalism of wave function is a mathematical construct because we can't see the wave function a priori, right? That the quantum particle is indeed in that state. We can only infer observables, measurements of observables, actually.
Right.
So quantum foundations deals with trying to understand what is real versus what we can observe. Like, what is the connection between those two?
And I just want to go back to something a word that you said a few sentences back. You were talking about trying to measure these quantum states, and you talked about doing that on many copies of the same state. But I think that word copy is maybe something we should talk about, because I think there's another interesting property in quantum mechanics that you can't actually make an exact copy of a state. Is that right?
You can't make an exact copy of an unknown quantum state. So that's no cloning theorem, actually. Like, once you know what is the quantum state, mathematically, you can prepare many copies of it. But if you don't know what is the quantum state of a particle, you can't copy it. And that is a principle that would be used in many different types of applications of quantum information and quantum computing, actually, like quantum cryptography.
And that's different than in classical cryptography. Is that right?
Yeah, like in classical cryptography, like, if you take out the measurement, like if you get a measurement of you can create copies of something basically in quantum classical cryptography without other people knowing about it, actually. But quantum state, like as soon as you measure, the quantum state of particle is destroyed actually. So once it is destroyed, the receiver end will know that it has been intercepted by some Eve, actually.
Is that the quantum cryptography or the idea of quantum encryption that measuring a quantum state changes it and therefore you can detect whether it's been measured?
Yeah, that's right.
So, and that's sort of a branch of quantum computing and quantum information. I wanted to get back to that because you said you work at these intersections of quantum information, which is related to quantum computers, which are, in theory, these very powerful computers that harness superposition. And but you said you're at the intersections of quantum computing and quantum foundations. So, which questions are currently sort of the focus of your attention? What are you trying to figure out?
So I became interested in chaos actually. So initially I did a few projects during my undergrad studies in the field of classical chaos. And then I did a project in the field of quantum chaos.
So can you actually just start by telling us what classical chaos is, maybe before I know that's not really what you work in, but it might be useful to start there.
Chaos is a pretty loaded term non-scientifically, but chaos is a very specific meaning in your...
Many people would be familiar with the term butterfly effect. So it is like, can the flap of the wings of a butterfly in Brazil cause a tornado, say, in Germany? So that's the butterfly effect. Can very, very small initial conditions change in very small changes in the initial conditions lead to vast differences in the outcome, actually. So chaos is basically unpredictability due to sensitivity to initial conditions. This was like the seeds of chaos theory were sown by Henry Poincaré, but then it was well formulated by a meteorologist, Edward Lorenz, around 1960s. He built a weather model.
Sorry, a meteorologist came up with chaos theory?
Yeah.
Okay, I didn't know
right.
that. Is weather and meteorology, that's classical chaos theory? That has nothing to do with quantum?
Yeah, that is right. Like in classical so chaos is basically a property of classical dynamical systems. Like not just physics, like any kind of dynamical systems you want to predict. Like for example, the population of fish in a pond, or weather is another example. And then even in a stock market or something like that, chaos has applications in so many fields actually. So dynamical system is basically any system that evolves with time.
Sorry, you said a dynamical
system. It's any system that evolves with time. And so you basically have either differential equations, like you have a set of variables. For example, for weather, you can have variables as temperature, pressure, or something like that. And differential equations telling us how those evolve with time, basically. So now these differential equations, if they are nonlinear, if they non-linearly depend on the other variables, then it results in a divergence of solution. Sorry, divergence is the wrong word. But
you're saying that weather can be an example. So is this why I might sometimes look at my phone and see that it's supposed to rain tomorrow, but then it doesn't actually rain? Is that because it's very difficult to predict? Is that related to the fact that it's a chaotic system?
So weather is a chaotic system. That's right. So the thing is, like, we all know that we can't really predict the weather of any place. Like, for example, if we look at the weather of Waterloo today, how is it going to be tomorrow or day after? And we see that many times it's not the same as what it is tomorrow, right? So why is that the case? We have advanced technologically so much, but still we can't really predict the weather a few days in advance of any place. If we had predicted, like, if we could have predicted, so many catastrophes on Earth could have been like avoided or not avoided, the destruction could have been
Yeah,
avoided.
if
For
you knew a
example,
hurricane was coming a month in advance rather than a few days in
yeah,
advance, you'd be
something like that, a
grateful for
cyclone or
chaos theory.
something. But the thing is, they are predicted only a few days in advance with some probability that this could happen. So it is because like these models are non-linear, so they can't be solved exactly, and they can exhibit chaos that whatever initial condition we input, for example, the temperature or pressure, whatever we input in the bunch of, for the variables in the bunch of differential equations, those variables will have some error in the last digit at least. Like if we have 5-digit precision in our value of the temperature, there is a small error in the 5th digit after the decimal, right? So that very small error in the last digit actually can amplify upon evolution of the system.
Right.
The more precise we are in
Longer
the initial variable,
string of digits after the decimal
yeah,
is...
the longer we can actually predict the weather to like the likelihood of the weather in advance. But it will lead to unpredictability after some time, no matter how much precision you give in. Like there is going to be some error in the end, and that will lead to unpredictability in the long term. So that's why weather is an unpredictable system. But that's the thing, weather is a very complex model, and it may look like chaos is a property of very complex models, but that's not true. Even very, very simple systems, for example, double pendulum is chaotic. So double pendulum is basically like you have some simple pendulum in which you have a bob attached to like some knob, which oscillates in a plane. Now you attach one more bob to the end of the first bob.
So I have kind of a stick or something with a ball on the end, and then I have another rod attached to that with another ball on the end.
Yeah.
And it can swing independently of the first, right? The first ball can swing, well, not independently, but affected by. Yeah.
They will be dependent in some way, but overall, the motion is chaotic actually. Like you can search various YouTube videos actually that...
They're really fun to watch, by the way. Double pendulums, good hypnotic entertainment.
Very small initial condition change can lead to high unpredictability actually.
Cool.
So that's the thing, that chaos is not just a property of complex systems, but very, very simple systems can exhibit chaos.
So I want to ask something here just to make sure I understand. So you're saying with weather, if I'm, say, measuring the temperature, it might be, say, 20 degrees Celsius, but I'm not sure if it's 20 degrees or 20.0001 degrees Celsius. This seems like a very small change. And if it was a non-chaotic system, maybe the result 2 days later wouldn't depend so much on whether it was 20 degrees Celsius or 20.0001. But because it's such a complicated system that's non-linear and we call it chaotic, it's in the end going to depend a lot on that really small difference in that variable. Is that correct?
Yeah, that's right. So that small difference in nonlinear systems could in principle amplify to very large differences in an unpredictable manner. But if it is a linear system, or if it is an integrable or regular system, like different words for the same term, then those small differences won't amplify a lot actually, or it will amplify in a very predictable manner. If it will amplify, like there can be unstable bounded systems in which things can amplify, but we still know how it amplifies. So
may I jump in? A quantum system, is that more complex or less complex than weather? Quantum being very small and there's parameters around it. What does quantum chaos refer to?
So quantum chaos has not been very well understood yet, although it's been like 100 years of the development of quantum theory. And why is quantum chaos and quantum classical correspondence is an important problem? I'd like to give another example. For example, Galilean relativity was well known from a few centuries, right? And then came in a special theory of relativity, where the speed of the object can be very, very high. Now, as you start reducing the speed of the object towards normal speed, special theory of relativity very smoothly merges into Galilean theory of relativity. It's not like Galilean theory of relativity is wrong, right? It is still right at the level we observe our everyday world. So then this new theory of relativity was formed.
By
and
Einstein?
Yeah,
Okay,
that's right.
I got that one right.
And then it smoothly merged with the old theory, where the old theory was predicting things very well in normal circumstances, which we can observe through our eyes. Likewise, classical physics can very well predict our everyday world that we see around, most of the things. And then quantum theory is something that describes phenomena at the microscopic level or at levels which does not happen in normal circumstances. For example, very low temperatures, temperatures near 0 Kelvin or something like that. We don't really see that. So, for example, this superconductivity. So you can see the effect of superconductivity at a macroscopic level. It's a big object visible through our eyes, right? And we see that, but we can't.
Like a levitating supermagnetic train or something like that.
Yeah, that's right. So that happens at very, very small temperatures, although it is macroscopic, but quantum mechanics is the thing that predicts it. But the thing is, there has to be something different from normal circumstance where classical physics fails. For example, very low temperature or microscopic scale in terms of like size of an object or something like that. So quantum theory explains the microscopic world or the world or other circumstances where things are very different from what we observe in day to day, like temperature or something like that. And then classical physics explains our everyday world. So in principle, quantum theory should merge as we scale up the size of the object or as we'll scale up the temperature or something like that of the system. Quantum theory should very smoothly merge into classical physics, and we should be able to understand that convergence, because classical physics is not wrong. At least we know that know that most of the things around us could be predicted using classical physics. So this is the field of quantum classical correspondence, and it is more or less fairly understood for integrable or regular systems, but for chaotic systems, it is not still understood. So
why is that? Is it just because it's an extremely difficult subject? It's difficult to measure. You're dealing with tiny microscopic.
So there are fundamental differences in the formulation of quantum mechanics and classical physics, actually. So in classical physics, chaos occurs like we see chaos through trajectories actually in phase space. Like phase space is something like you take the position and momentum of a particle and then track how the position and momentum evolves, and it will curve out a trajectory in the phase space.
And what's a trajectory? Just kind of the path that it follows?
Paths, yeah, that's right. But not just position. You have to add, there is another axis, which is momentum. So in general, when we see a particle, it's just position, right? But there is a momentum associated to the particle, which is, for normal particles, it is mass times velocity. So that is another axis. So the phase space is formulated by position plus momentum. So classically, it is possible to measure the position and momentum of particles precisely. And the chaos occurs in the fine structures of the phase space carved through these trajectories, actually. But quantum mechanically, due to Heisenberg's uncertainty principle, we can't have precise values of position and momentum at the same time. So we don't have trajectories in quantum mechanics just like the way we have it in classical physics. So this is one of the fundamental reasons we can't take up the definition of chaos in classical physics and use it in quantum physics, actually. So just because quantum physics is formulated in a very different manner than in classical physics, so understanding chaos in quantum physics the same way as it is done in classical physics is not possible. But there should be, as I talked about earlier, there should be a smooth convergence of quantum physics into classical physics as we scale up the size of the object or things like that.
And I know that your work in particular is trying to understand the connection between chaos and quantum entanglement. So can you, maybe before I ask about that, can you tell us about this mysterious feature of quantum entanglement?
So, and as I had told, like in quantum mechanics, the superposition and entanglement are two purely quantum properties not there in the classical world. And entanglement is like if you have we were talking about quantum coins. So if you have a couple of quantum coins, like classically you will have, if the coin is classical, if both can be in heads or both can be in tails, or one can be head and one can be tail. But quantum mechanically, you can have a state like a superposition of head plus tail, something like that. And when you measure one of the coin, if the pair of quantum coin is in this state that I talked about, head plus tail, then if you measure one coin and if it comes out to be heads, the other coin is bound to give heads when you measure it. Likewise, if the first coin comes out to be tail, when you measure it, the other coin is bound to be give the result that it is in tail state.
And this is even if the two coins are far away from each other,
Yeah,
handled by separate people. This is what Einstein said was spooky action?
Yeah, that's
where it
right.
seems like one thing far away is happening at the very same time as a different thing. I know that's probably not the scientific explanation, but is it fair to say that that's one of the things that we just don't experience in our everyday lives?
Yeah,
so we have a hard time wrapping our heads around it?
Yeah, that's right. So that's the thing, that if you prepare these two quantum coins and person A, suppose you give one of them to Alice, other of them to Bob, and if they are prepared in this joint quantum state, entangled quantum state, and Alice suppose goes to Australia and Bob lives here in Canada, and then Bob measures his quantum coin, and if he gets heads, and then instantly Alice will observe, if she makes a measurement on her coin, that it is in head actually. Likewise, if Bob gets tails, then Alice will see it to be tails. So that's the thing, like
that is spooky.
That is spooky, and that's the thing that we have observed. This is called non-local correlation, because it's not like a measurement in Canada is affecting something in Australia and instantly. So, and we know that information can at most travel with the speed of light. It can't travel beyond that. So how does this happen? So that's why it is called non-local correlation. So the thing is, like, this is very surprising that this happens, but it is found to be true in several experiments actually. Mm-hmm. So, and it is still a question, like, how does this happen? How do we understand actually that this happens? It is very, very surprising in that way.
It seems like there are a number of mysteries that still need to be solved. And you mentioned sort of the big one of, at what point does the quantum world sort of move into the classical world that we inhabit? And why is it so hard to sort of pin that down, that making general relativity and quantum mechanics play nicely together? Because that seems to be the focus of a lot of work, is understanding the change between quantum and classical.
So these are two different questions,
okay.
Actually. So.
Well then, yeah, I can rephrase that. So I guess I'm getting at this question of understanding where quantum ends and where classical begins, and why there's not sort of a total agreement there. Why is it so challenging to find this I guess unified theory?
So, like, quantum classical correspondence, that's why is an active area of research actually. Yeah. Like, And we don't have an answer to that, I guess. Why?
Maybe my follow-up question is then, it's for decades people have been working on this challenge, and it's a big challenge. Is it not daunting as a scientist to take on challenges that are so unsolved for so many years?
So it is unsolved for so many years, but it's not like no progress have been made. Like there have been so many different kinds of properties that we see are different for, like we can classify systems whether they are using classical mechanics, whether they are integrable or not, or chaotic or not, depending on like whether the system has a classical analog. So there are several quantum properties that people have come up with in these studies where they see that they behave differently when the classical analog is integrable or chaotic. But all of these properties, what we have found is there is some exception. And physics is a study, physics is a like field where most of the innovations happen when we see an exception actually. Like if we had thought of photoelectric effect as an exception, studied it separately, that it doesn't follow the rule of classical physics, we wouldn't have this theory of quantum mechanics now, right? So whenever you see an exception, that is the area of growth. So like
Interesting.
so many advances have happened, but we still do not have a single answer. And there is a possibility that after a few more years or after a couple of decades or something, there are so many pieces of these puzzles that people have found. There will be someone who can glue all of them together and find an answer.
Might it be you?
Hopefully.
Is that a hope, that a sort of professional goal that over your career you will move this field forward a certain amount?
I mean, I started my research with that goal actually, and I have made small progress in some of the questions or conflicting answers. And I hope that is the big goal actually, that I hope someday if I can answer like how quantum classical correspondence happens in chaotic systems, like that is a big goal.
Yeah.
I hope someday, if possible me, that's fine. Like otherwise someone answers that questions.
And so why did you choose to come here to the Perimeter Institute to kind of help make progress towards answering that question?
So Perimeter Institute is a place where like there are so many, it's a theoretical physics place, and being a theoretical physicist, like a perfect place. And then other thing is like there are so many different areas of research here, and people like so freely collaborate with other people in other areas, and these intersections are most interesting actually. Like I started my PhD, I wanted to work in quantum chaos, but then my advisor had worked in quantum information, so she gave me like this problem of understanding quantum chaos through this quantum information perspective actually. And then I got into the field of quantum information. And then here like we have different fields, like I have collaborations with other postdocs in quantum foundations and condensed matter. So those intersections are really interesting, finding people from other areas. And it's a very active place in the sense that there are so many visitors from all around the world actually, like giving talks on so many different topics. So using techniques and tools from one branch to other branch, that's where I think sometimes major innovations happen. For example, like quantum information is one thing that has led to like the tools and techniques in quantum information has been used from condensed matter to high energy physics actually. Like black holes also, you have this black hole information paradox or something, and in condensed matter you have these questions about thermalization, ergodicity, and where like tools and techniques from quantum information have been used to answer some of the questions. So these intersections are really interesting, and that happen a lot at Perimeter. So I'm really excited to be here and collaborate with other people.
That's
Yeah. Oh, sorry.
fantastic. I wanted to ask, a little bit further back in your past. Were you always, since you were a little kid, interested in quantum physics? Or how did you find this career path?
So I think it started in my high school that I became fascinated with physics. I think in my primary school I was more interested in maths. I think I had an analytical mind and always took a delight in like solving problems, difficult problems actually. Like
I read that you would solve problems, logic problems from a magazine.
yeah, that's right.
Yeah, just on your own, just for fun?
Yeah, it was mostly for fun. I had elder siblings who were preparing for um, general competitive exams in which there were maths and logical questions actually, and it was fun to see whether I could solve them in my school. So that happened, and then in my high school, like I was preparing for a national level engineering entrance exam. Um, and in that exam basically the problems that were there were very complex. Like it was not just formula based that you are given a problem and you have these variables and this is the formula, you plug in the variable values and you get the answer. That is not the kind of questions. Like it, you had to think from first principles actually to solve those complex problems.
Mhm.
So I was preparing for that exam, and like I was I had joined a coaching class, which was very usual back in India.
Coaching for this particular exam, like tutoring to learn how to take the exam?
Some like so high school students. One thing is you have to give school exams like board exams,
Mhm.
and then other thing is you have to get into a college or university after that. So these national and level entrance exams, basically like these coaching classes, they taught things at a more fundamental level, some of the coaching classes, and like board exams was slightly simpler in the sense that, as I said, you can have variables and plug in a formula and you will get answer. But to quantify, to crack these entrance exams, you really needed to think from first principles. So the teacher, like my physics teacher in my high school, in my coaching class, played a very, very big role, I would say, uh,
Mhm.
where I became fascinated with physics because he taught us how to think from first principles, like given a problem which seemed very complex in the first place, and I would be like, there's no way I can solve it. And then when you start with these first principles, just like the very basic equation, which is F equals to ma, Newton's second law, well known as Newton's second law. So this equation, like if you understood this equation well, like there was so many types of problems that you can solve, very complex problems, and just seeing that everything combines together in this simple equation and you can solve difficult problems seemingly unsolvable in the first place, that gave me another level of delight, I suppose. And I enjoyed this, and the way my teacher taught, it I really imagined myself like I felt like I wish I could develop some of these equations or something like that that were so fundamental, using which you can explain so many phenomena in the world. So that really like made me think that I wish, pursue this research career in the first place.
And
And
where did you go from there? You went to undergraduate studies?
Yeah, so I cracked that engineering exam, national level.
yes, you told us, I believe, of the 400,000 people that took that exam, you're in the top, what, 1%, 2%?
Top 2%.
So you weren't going to mention that on your own because you were being too humble. But she aced the exam. Then what happened?
Yeah, so I was able to crack that exam, and then I went to an engineering institute, and I was there for a year, but somehow I didn't feel quite at place there. And I couldn't picture myself becoming a researcher after studying there. I don't know why. I just didn't feel like it. I still try to understand why that happened, and at the age of like 18 or something like that, deciding to quit a place like that and go to a new college was a risky decision, not supported by many. But I was not feeling at home at that place, and then I wrote an exam for another institute, undergrad institute, which was more research focused. And I qualified that exam, so I went ahead joining the other institute where I did a bachelor's degree in physics.
And I really want to ask something here because for those who might not know, I know, Meenu, you wrote such a really nice article as part of this story, What Is It Like to Be a Woman in Physics, which is a collection of stories by women here at Perimeter Institute. And I just wrote down one of my favorite quotes. You said, "It was not normal for a small town girl from a conservative society like me to leave home for undergraduate studies, let alone later travel to a foreign country for graduate studies." And the rest of your story is really great too. And I just was wondering if you can kind of speak to that piece a little bit. What was it like to make that decision to challenge those societal norms?
So I was very scared in my school time. Actually, like I was seeing most of the women around struggling. Actually, like I have a bunch of like very strong-headed women around back in my family or extended family, but I still see that trying to like break any social norm, like they have to put so much of effort, and after putting in so much of effort, little by little it breaks them down somewhere actually. And that hard life that I was seeing all of them living, I felt like I really need to have a better life which I can live on my own terms. So, and it was not normal for families back in those days actually to send their girl child to study outside of the hometown. Actually, it was not considered safe or something. It's relatively normal now, but in those times it was not that normal. So I was like, I really need to crack a very, like, if I could crack this prestigious exam called IIT JEE, it was very prestigious and it would be a prestige for the family. They will be willing to send me if I can crack this exam. So I put in a lot of hard work and effort, and I was very, very scared. What if I couldn't crack it? Like, I will be stuck here. So, but with hard work, I think hard work and conviction, I was able to crack that exam and leave home. So it was slightly difficult.
And home is a relatively, I think it's Gaya in India.
Yeah,
Gaya. It's more of a tourist place. I think it's a spiritual destination because there's connections to Buddhism.
yes,
It's
that's
probably not a place where a young girl says, "I want to be a physicist," and gets the warmest reception. What kept you going when you said you met opposition at stages along your way?
So I think, first of all, I really liked studying and solving analytical problems in physics and maths. Like, that was one thing. And the other thing was like that conviction that I want a better life. So both of those things, like, and the third thing, like, I really got amazing teachers, like these coaching classes I am telling about. Like, I had 3 different teachers who were extremely supportive, always there. So I think taking classes from them really, really helped, and they were there to answer my questions or support me um, in any way they can. So their presence meant a lot at that time. Actually, their belief in me that I can do something, I can crack this exam, even though it was difficult, that really helped. So yeah, due to those factors, I was able to make it.
Yeah.
Amazing.
And moving, from a small hometown to another city, let alone a country on the other side of the world, that was a bit. Was that moving to Canada to do a PhD? Was that a difficult leap for you to make, or was that always in the cards that you would go somewhere else to become a researcher?
I don't exactly remember when was the first time I really thought that I could go to a different country and live by myself and study on my own. That was not something that I thought from the beginning, but then in my college, I was the third batch. There were two more senior batches than me, and I was seeing other students, including women, going out to other countries and for research projects, summer internships, or for graduate studies. And I just felt like if they could do it, I'll be also able to do it. So I followed their footsteps in that way. So yeah.
And you created your own footsteps too, for others to follow.
Yeah, hopefully it will inspire others as well.
It's interesting, right? I think for so many people, it's so important to have those role models, right? Whether they be your colleagues that are a year ahead of you or somebody that's maybe already a professional in the field. Was it important to you to have role models at maybe different levels along the way?
Yeah, so my first role model, I would say, was or is Kalpana Chawla. Unfortunately, she is no more. She was the first Indian woman to go to moon, actually. And during her second trip to moon, there was a crash. So there were 7 astronauts in that um, in that shuttle, and unfortunately, they all passed away. She was a big role model for me. I think that she came from a small town in another state in India, which is Punjab, and seeing her, reading her story, knowing about her, I felt like if I followed her footsteps, I could do something as big as her. So that was really important. Looking back, I can never think that I could have looked up to Neil Armstrong, for example, and thought that I could have done something similar or something like that. But having someone who has same gender, same ethnicity, same family background, like similar kind of family background, and really influences, you can dream big if you see some other people with similar situation dreaming big and being able to make it. So in my childhood, I always dreamt of becoming an astronaut, just like Kalpana Chawla. It changed over time, but I think her presence and whatever she achieved in her life, knowing that, helped me dream big, at least in my life.
Yeah, that's amazing.
Amazing.
Would you, if someone offered you a chance to go to space, now that space tourism is a thing, would you want to be an astronaut still?
I think I'm less of a tourist and more of a person from research. Like if it was more of an opportunity to go there from a research point of view, I think I would be more interested rather than just going there and seeing things, how it looks like.
If you did have to now say what's your dream, what would it be? Would it be to crack this quantum classical correspondence?
Yes, if I could do or play a good enough role in that, in cracking that question, that would be really nice. But apart from that, all these innovations happening in quantum computing, I keep on thinking to the day, it sometimes it feels like it is a big dream which may or may not happen, but then I keep on thinking that about the time when classical computers were devised, like the first computer were like the size of a big room. And now it's like in our hand.
Yeah.
There-
Actually, at the Institute for Quantum Computing, where you were, some of the quantum computers there are the size of a room. It's a similar analogy.
Yeah.
Quantum computing is sort of at that infancy stage, but you can see the potential, and you got to work right in the middle of a quantum computing research center.
Well,
Yes, that's right.
I love the way you put it earlier, too, that sometimes doing research involves putting together so many little pieces of a puzzle, right? And you have these pieces, it's not always obvious how they fit together, and it's not always obvious how many pieces there are or how long it's going to take to put them together. But I think even figuring out how to glue together two pieces is a big accomplishment in many
that's
cases,
right.
right? Yeah.
Yes, I agree.
Yeah.
I'm curious to know if you still have that same joy that you felt when you were a kid solving puzzles. If doing math and solving difficult problems, is it still fun? Is it still like a hobby for you the way it was as a child?
Yeah, like whenever I get any new idea, Like, I'm very excited to try it out, whether it will work or not. That's the most exciting part of my research projects. Like, and these ideas just happen to come around like while I'm doing some stuff which doesn't require a lot of attention. For example, washing dishes or cooking or something like that, or waiting at the bus stop for the bus. So these are the moments when some ideas will just come to my mind, and then I'm so excited to try it out, whether that will work or not. And that is the most joyous part of being a researcher for me.
Interesting. Even if it doesn't work out, even if the idea falls flat and doesn't pan out?
So as long as a few ideas are working out of many, like as long as two ideas are working out out of 10, suppose, that's fine. It will be a little frustrating if I thought of 10 ideas and nothing worked out. But luckily, if I think of 10 ideas, 2 to 3 ideas turn out to work. So
Trial and error only works when there's some error. So yeah, you need to.
yeah.
Yeah, amazing. Well, Meenu, we now want to take some questions, if that's okay. So we, as part of this, we want to see what other people want to ask you as well. And so we have a question today that was actually sent in by a student from our PSI program here at Perimeter Institute. So for those that might not know, PSI is a 1-year master's program in theoretical physics here at Perimeter Institute. I actually teach in that program. I teach lectures in quantum science and machine learning. So we have a question here that's from one of our students named Anna Knur.
What does it mean to do research through the lens of quantum information? Do you really think the world can be reduced to only information?
First of all, thanks a lot, Anna, for that question. That's a great question. So the thing is, in my research, since I started my PhD, I started working on quantum chaos through the lens of quantum information. So that has been a majority of my part in my research. So I can't really speak of in general terms what it means to research from other perspectives a lot. But the thing is, quantum information, I see it as something that has brought together different fields, as I told earlier, in physics. Like it has provided a new perspective in different fields. For example, in condensed matter to high energy physics, which in general are look like distinct topics actually in the first place. Like if you go back like 30, 40 years ago, all those physicists, you can classify them as condensed matter physicists or high energy physicists. But now that's not the case. For example, I would talk about a faculty here at Perimeter, Benny. Like he works at so much, like he is very much into
Benny Yoshida?
Yeah.
We know
Jinx.
Benny.
Yeah, so he works very much into high energy physics, like black holes stuff, as well as condensed matter physics, and he is a faculty in the quantum information research group. So that's the thing, that looking at things from the quantum information perspective gives us more pieces of the puzzle, the bigger puzzle of physics actually, and it definitely helps, and maybe it will be a piece that solves bigger problems in physics, who knows.
Yeah.
So it's not necessarily about answering every possible question, but giving a new way to look at, or a new perspective. Yeah. Oh, cool.
To the existing problems in
Yeah.
other fields of physics, actually. So it's definitely an interesting way. I have been working in it for 7 years now, since the start of my PhD, and I have really enjoyed it.
Yeah.
Amazing.
Amazing.
I have a question from someone named Ahmed, a student here in Waterloo region, and he asks, why can't quantum mechanics agree with relativity?
Thanks, Ahmed, for that question. So the thing is, in general theory of relativity, space-time is continuum, and energy is also continuous. But in quantum mechanics, space-time is at equal footing in general theory of relativity, and energy is a continuous thing. But in quantum mechanics, at least in the Schrodinger, if we talk about the Schrodinger picture, space and time are at different footing. Plus, energy is discrete. It is quantized. And other thing is like we still do not have a quantized theory of gravity.
Mhm.
Like those pieces are required such that we can glue together like general relativity and quantum physics.
Is that quantum gravity? That's
The bigger umbrella,
Yeah.
in which people are trying to figure out how to quantize gravity so that we will be able to glue together these two fields.
So there's a whole field of research devoted to answering
That's right,
that
and there
question,
are
I guess. Yeah.
many faculties here, I guess, working in that area.
Well, Meenu, you've been so generous with your time, and it's been really fascinating chatting with you. Thank you for joining us. It's been great.
Yeah, thank you. This has been just so much fun. I've really enjoyed learning more about you. Even though I've known you for years, I've learned so much about you. So thank you so much for sharing your time with us.
Thanks a lot, Lauren and Colin, for having me. It's really great to chat with both of you.